Hello, welcome to this presentation about programming for 3D modeling. I will share some slides first, and then I will go very quickly through the slides because then I want to show you a hands-on example. The example is in the repository, so you can pull it from the repository already. I pushed the latest version this morning from the train. The example is for voxelating a cone object in Rhino using Rhino 3D Python 3 component. And you can open the example and see the full code, complete code, but you can also try to do it now if you dare to follow me online. But I think we don't have enough time for doing that. So I will leave you to do it afterwards. And right now, I just want to go through some basic concepts of programming. Okay. So first of all, Python is an interpreted language. It's very important that you use the right interpreter managed inside a Conda environment. So I have explained these details for setting up Conda and Visual Studio Code in one of the videos that I've shared with you. I've shared a link to it. And the interpreter of Python is a python.exe file on your system. And a Conda environment is basically a folder that has all the libraries that work with that particular version of Python in that folder. And Conda is a package manager, so it takes care of the compatibility between all the libraries that you install. And so the proper way of using Python is with Conda. That said, however, the Python 3 component that you have in Rhino 8 is a great tool. It's the first Python 3 component in Rhino after many years people asking for it. It's a great tool that gives you access to a great geometric library, but the only issue that I have with it is that the Python environment of your code component cannot be managed with Conda. It can be managed, however, with pip. Pip is also a package manager, so it can help you install some packages. I have added one component and the code for installing NumPy and other libraries in the Python node of Grasshopper for Rhino 8 in one of the files. You can also see in the file that there's a little trick for it to call libraries and add them to your Python component. Okay. So it's important to know that the reason why we're using Grasshopper or Rhino in this case is the geometric library of Rhino. Would use a little bit of Grasshopper because of some utility functions that Grasshopper has for visualizing stuff. Together, Rhino and Grasshopper provide a very nice environment for you to learn the basics of 3D modeling. For professional practice in the field of geospatial computing, I don't think you can use Rhino and Grasshopper for production code, but you can prototype your codes inside Rhino and Grasshopper. For production code, you can use the libraries that we are introducing to you in the notebooks. Those are the professional libraries for geospatial computing in 3D. Yeah. So, but I think for educational purposes, this is a perfect environment because it gives you access to a very complete geometric library compared to the libraries that we are using in the notebooks. The library of Rhino is much broader in terms of functionality, the methods that operate on objects, and also the variety of the kind of 3D objects that you have. Okay, is everything okay in the online If there's a problem with the slides or whatever, please do.
It's small.
Are you sharing anything on the screen?
Yes.
Oh, then yes, there is a problem because I don't see it.
Oh, okay. So
Sure, the screen.
is it working here?
Yes. Now I see it. Thank you.
Okay. Thank you for letting me. So there's nothing very important here so far. Just a bunch of statements. Okay. So far I've told you some basics of linear algebra, and I'm going to tell you a bit about the fundamentals of Python. First of all, data types, the most important thing, and logical operators and flow control mechanisms. Basically, if you understand these few things, you know enough about Python. The rest is practicing. So basically, data types and flow control. Let's put it this way, right? What is flow control about? If you don't have flow control mechanisms, then you cannot have algorithms. Everything is just a sequence, a trivial sequence of doing this, then doing that, and going further, right? So if you really want to learn programming, think about a cursor, a blinking cursor on your screen that is waiting to execute the next command. If you don't have flow control mechanisms, it goes to the next line, to the next line, to the next line. With flow control mechanisms like for loops, while, and if then conditions and so on, you can tell the cursor to wait for a couple of times until a loop is finished, or wait until the while condition is true, or whatever. And you can direct the flow of the execution of the code to somewhere else. So that's the meaning of flow control. So essentially, algorithms are just about data types, doing operations on the data types, and controlling the flow. We call an algorithm if it is a non-trivial sequence of operations with complex flow, right? And algorithms are then step-by-step computing processes with non-trivial flow control mechanisms. Yeah. So logical operators are very important because deep down, all the data types that you have in digital computers have something to do with Boolean or logical representation or binary representation of things, numbers. This is a very important thing to note. All the numbers that you represent in computers are actually binary numbers, deep down. So the most important implication of this for 3D modeling is the following. In the world of high school mathematics and so on, you think about real numbers and continuous spaces, but real numbers don't exist in computers, in digital computers at least. What does that mean? That you will always have some issues of precision with representing points and vertices in your objects. Therefore, you always need to have topological primitives to correctly associate items or vertices in your objects together. Yeah. So that is why in 3D programming, instead of talking about real numbers, we talk about floats or doubles or singles or whatever. These are all representations of they're almost like real numbers, but with limited precision because you have a limited space in the memory for representing these numbers. And therefore, they have different names. We don't call them reals. There is no such thing as a real number in a computer. Because to represent a real number, you need to be able to represent rational and irrational numbers with unlimited precision. And there's no such thing as unlimited precision. Float numbers have a limited precision. And this is the fundamental reason so many things go wrong in geometric computing, right? So there is no geometric computing without topology, and you need to always keep that in mind. And what are data types? Data types are like containers that are appropriate to contain the data that they carry. I showed you already some very simple data types, which were basically tuples of numbers. Tuples of 6 numbers to represent lines, tuples of 6 numbers to represent planes without an orientation, tuples of 9 numbers to represent planes with an orientation, and so on and so forth, right? And these numbers were float numbers in Python. And you have methods to operate on these data types. So data types are typically objects. Python is an object-oriented programming language. You can define new objects, and what a 3D geometric computing library is basically a bunch of data types with methods that operate on those data types. So this is important to keep in mind if you want to work with multiple libraries, like what we are doing in the afternoon with the notebook. You have to be able to translate one data type to another, because you have data types like in a mathematical sense, and you have data types in the sense of the exact object definition that one library uses versus another. So the exact representation that a library like Open3D uses for representing a mesh is different from that of Rhino. But essentially, deep down, both of them most probably represent similar things, at least, like vertices and faces. Or for a line, they both require 6 numbers, right? So if you know what needs to be represented in terms of the sufficient information content, you can translate one data type from one programming language to another, right? And it's very important to focus on primitive data types. Primitive data types go even beyond one programming language and can be shared with other programming languages. So the float representation of numbers in Python is not very different from the float representation of points in C# or NumPy. Yeah. By the way, NumPy is effectively another programming language. That's the programming language that we're using in the afternoon. Everything in NumPy looks like Python. It is practically Python as far as you're concerned in terms of installations, but it's more than a simple library. It actually changes the whole space into another space, because the data types of NumPy actually come from a programming language called C. So NumPy has its own data types, like integer 32 bits and integer 64 bits, and so on and so forth, right? So when working with NumPy, think about these primitives and make sure that you're representing things with the right primitive. Okay, so what are the primitive data types in Python? These are the first 4 are the most primitive data types: integers, floats, booleans, and strings. I think it's pretty self-explanatory what they are. For representing words and sentences and so on, you work with strings, but in 3D modeling, you're going to be mostly working with floats for representing vertices and geometric things, and with integers for representing topological things. And with booleans, you will be representing conditions, right? And the hashables, the so-called hashables, are collections of things which are indexed. So you have lists represented with square brackets, tuples represented with parentheses, and dictionaries represented with curly brackets. And they're all quite useful for representing geometric objects. I have already shown you the use of tuples for representing a collection or a bunch of points or numbers to represent vectors, rays, planes, and so on. With lists, it is obvious that you can represent collections of things. It's the first choice usually to represent collections of things as lists. And with dictionaries, you can do one very important thing, which is representing things that are uniquely indexed. So actually, the example here is not a perfect example. Dictionaries have keys, so they're kind of like real good old-fashioned dictionaries that have chapters with a key. So an object in a dictionary is represented with a key, and the best kind of keys that you could use for bookmarking chapters in the dictionary are integers, if you ask me. is with integers like spatial indices. You know what spatial indices are, right? In geographical information systems, spatial indices index the entire geographical space into integer numbers, basically. So these are very good things for representing chapters in dictionaries. Yeah. And you can refer to the items within these kind of variables, collection variables with the index numbers or addresses, which always starts from 0. Always keep that in mind. And assigning value to things in programming is always done with an equality sign in most programming languages. And that confuses people a little because this equality is not about checking equality, it's about assignment of a value to a variable. If you want to check equality, then you use 2 equality signs in Python, like in most other programming languages. And Python is a little bit different from the more strict programming languages like NumPy, like the one we're going to use in the afternoon, because it's a dynamically typed language. So the types of things are not explicitly declared. But C# or NumPy and most other programming languages work with explicitly typed data. So be careful and make sure you know exactly what type of things you're dealing with, right? So everything has to have a data type. So, okay, as I told you, with 2 equality signs, you can check whether a statement is true in terms of the equality of the left-hand side and the right-hand side. So this is about checking equality, and all kinds of these tests, like whether something is larger than something or smaller than something or equal to something or not equal to something else, result in Boolean values. So I have a quick question for you. If you wanted to check whether 2 points are equal to each other, would that be as simple as this, or is that philosophically different? Can you think of performing an equality test for 2 points?
No,
Yes,
it's different. You check their position by XYZ.
yes. And do you have to make sure that their XYZ coordinates are exactly the same, or
Yes.
they're more to?
No, yes. If they're equal, then they should be exactly the same.
What if they're only different in terms of the, I don't know, the 20th decimal?
Well, then you, I guess, set the
distance threshold, right?
well, yes.
Yes. So that's the core issue as to why some operations in geometric computing go wrong, because you often assume that things are equal to each other because they look equal, but after you do one transformation or after you export data from one format to another, in one of your applications, your integers have 64, your float numbers have 64 bits of precision. In the other one, they have 32 bits, right? That means their precision is different. And let's say you have done some transformation to your data from one coordinate reference system to another. So you've multiplied a bunch of matrices and your coordinates change a little bit. And that little bit makes everything wrong, right? Because those points are not equal anymore. And that's the core issue of topological computing. So you need to have, you need to capture the relations between objects independently of the position of the objects, or at least based on some notion of tolerance in terms of distance between objects. You have to have some definition for equality between objects, which is geometrically informed, but not so sensitive to such issues with number representation. Yeah. And so do you understand this line in the middle? A equals to 1 equal 1. What is going on here? We are assigning
1 to A and 1 equals 1.
what is happening. Actually, I would prefer to put 2 parentheses on the 2 sides of 1 and 1. that would make it a little bit more explicit as to what's going on here.
You are like you are checking when equal to, and then you are saving the boolean also.
Exactly. So we are assigning a Boolean value to the variable a, right? And so this shouldn't confuse us. This doesn't look like a mathematically correct statement, but it is perfectly fine in Python, right? And as a matter of good practice, I would put parentheses on the two sides of 1 equals to 1 to notify the reader that this is the whole thing is being evaluated first inside the parentheses and then assigned to the variable a. And this should be clear also, the logical operators or, and so on, right? Or the only thing that I want you to note is that or is equal to whether or in plain language. So whether this one is true or the other one is true, the result will evaluate to true. There's also another kind of or, which is called the exclusive or XOR, which is either or in plain language, right? So either one of them is true or the other one is true, but not at the same time. Can you think of the importance of the most important thing about Boolean operations in 3D modeling? Like doing a Boolean operation in terms of set membership on objects will effectively change objects. Like think of the intersection of two meshes. All the points which are at the same time members of both meshes at the same time, right? Will be the geometric intersection of the two meshes, right? You can imagine the meaning of Boolean operations on geometric sets of points. So always think about geometric objects as point sets. Then you'll have an easy time understanding what they mean, right? Point sets and equations that define what is special about that point set. What kind of condition is met by all the points in the set, or the locus definition. Okay. Flow control mechanisms, as I told you, are in Python for loops, while loops, and if, else if conditional statements. So basically, if you understand the data types and if you understand the flow control mechanisms, you understand the most essential things about Python as a programming language. The rest is practice and reading documentations and searching online. One important tip about searching online for problems, when you want to search for a problem about 3D modeling, don't search ITC 3D modeling course, Python, how do I do this? Search always Python, how do I do this? Yeah, that's probably the most important lesson that I can give you in terms of programming. Because nowadays you have Google and you can search for things, but it's important to know how to search and where to search. So if you are looking for good answers, you should look in good places like the Stack Overflow website and check the documentation of the programming language itself, like Python or NumPy. And it's probably also handy to have a couple of cheat sheets at hand to know all the tricks. But you don't have to, it's not like 20 years ago. 20 years ago, if you wanted to learn programming, you had to study a very thick book and go to a cave and come enlightened out of the cave after 6 months. It's not like that anymore, right? In 5 minutes or 1 hour or 2 hours, you are basically in the game. You just need to know how to search for your question. And please start, if you want to do something serious in programming, start forming a profile for yourself on Stack Overflow and learn the rules of the forum for asking questions properly, because they are very strict in terms of how questions can be asked and making sure that the questions have been have not been asked before and you have done your homework in searching through the website. Okay, so the most important thing that you need to think about when you are thinking about an algorithm, writing an algorithm, is that concept of a cursor, blinking cursor. If you can follow mentally what is going to happen to the cursor going through your code, then you understand your algorithm. So can you think about the cursor now? X equals to 14, this is an assignment. If X is smaller than 5, print X is smaller than 5. Is this going to happen? So the cursor is not going to here because after evaluating X is smaller than 5, it will be false. So it will be moved to the next one, which is elif or else if. It will be checked if X is smaller than 10. Will this be executed? No. So we follow the cursor to the next one. Will it be less than 15? Yes, true. So it will evaluate to true. Therefore, we go to the scope of this flow control mechanism. It is very important to understand the concept of the scope. Now you see the scope clearly highlighted as an indented scope in the text. This is a plain text file, right? So all the highlighting of colors, color coding of these different terms is done with the help of a so-called integrated development environment or IDE. So this is a sugar-coated piece of text, let's say, right? Without that, it's just a bunch of text, which is going to the interpreter of Python, and Python has to understand the scope of flow control mechanisms. What is the scope of this elif? This print statement, print X is smaller than 15. So within this scope, only things will be executed that have been known either in the global scope of the whole program or in this scope. And you are here because you are directed here with this elif statement. Yeah. So keep an eye on the scopes in your Python code, which are always indicated with indentation. In some other programming languages like C-style programming languages like C# and so on, the scopes are indicated with curly brackets. Yeah. And so now we are in the scope of the while loop. While this condition is true, while X is larger than 1, we are here. So when X equals to 10, we are here. We go here, print X is bigger than 1, and we do this, which seems strange from a mathematical point of view, but again, this is not equality, this is assignment. We make X 1 less than what it was, and then we come back here. This is the flow control mechanism, remember? So our cursor is back here. Now X equals 9 because 1 has been subtracted from it, and then this happens until X equals 1, which makes this statement evaluated to false because 1 is not larger than 1 anymore, and then we stop, right? So no magic, just following the basic principles of flow control. Okay. You can write for loops in Python in two ways. One is with explicit indices, like using lists of indices like this one, or using a range statement instead of while, or you can just say for some value in a list and just give the name of the list, and then it will iterate through the values. And obviously this is for discrete lists of discrete objects, right? I'm emphasizing this discreteness because sometimes I realize that people are trying to do the impossible thing, which is iterating through infinitely many things. That's not possible in digital computing, right? So you need to be aware of this fact that this is always about discrete list of things. Yeah. Okay, so what do you need to know to find your way through a typical piece of code for Google and Stack Overflow I told you about, and then you need to know your libraries. So this is about Rhino and Grasshopper, so therefore I'm talking about the resources for Rhino. The most important one is a library called Rhino Common, which is a library of geometric computing codes, and there are some other resources for getting started with programming on the website of Rhino Common. So you can just search for Rhino 3D API online or Rhino Common and you will find it. Similarly, for all the other libraries that we are using in the afternoon, we have quite a few. You have to consult their documentation online first and try to find the answers to your questions there. If you cannot find it, the next thing to resort to is to go to the Stack Overflow website and search again, and or just search Google for it. This is a relatively old picture of the possibilities for programming in Rhino and Grasshopper. For C# Visual Basic and Python Visual Basic is kind of deprecated now. It's only available as a legacy option. I have included a C# example for you in the example file. If you're curious about it, it's a programming language, and you can see the similarities and differences with the Python code. And you have a Python component, which nowadays allows you to code in Python 3. But I think I mentioned it that the environment cannot be managed with Conda, and it has to be managed with pip. There is an example to show you how you can install libraries like NumPy and so on in that component for Rhino 8 in Grasshopper practical. Don't worry so much about learning Rhino or Grasshopper. Rhino, when you open it for the first time, it shows you some getting started tutorials. Basically, if you follow them, you're there, and you just need it for visualization. Grasshopper is the same, and there's a short video that you can follow for 1 hour. I can give you a link. You will know whatever you need to know. You just basically need to learn to use one component, which is the Python component, and that's it. Okay. So how are we doing with time? So now I'm going to explain you this piece of code. Maybe you can open your Rhino and open this code example and look at it and play with it. You can copy for yourself. Maybe you can actually fork the whole repository and pull it to your system and open this in Rhino. There's a Python code example. You can open the Grasshopper file. Inside that, there's a Python node. Inside that Python node, there's this Python code that does this. And then I can explain to you what is happening here. I can also show you in the example file itself, but first I can give you an overview of what is happening in that file. This is an example for voxelating a cone. Cone-like object is a boundary representation which is closed. So we can call it a solid. It has an inside and outside. We voxelate it in terms of sampling it regularly with points. And these regularly sampled points are called voxel centers. And then for each of these voxels, we create a little box as a mesh. And we attribute the distance of this point to the cone object to every one of these voxels. And we color the voxels or the voxel points or the voxel boxes or voxels with respect to these distances using a range of colors from the minimum number to the maximum number. And we make sign distances by changing the sign of distances of the voxels that fall into the cone as negative distances and keeping the distances as positive for those voxels that fall outside of the box. So quite a few geometric operations. I want you to think about one of them in particular, which is finding the distance of a point to a cone. How do you think we can do that? It relates to one of the things I asked you in the morning. The distance, for computing distance, we need a path. And that path should be the shortest path, right? Otherwise, the distance of one point to an object is kind of undefined, isn't it? Right? So we need a point that is the closest point to that point that we are interested in on the object.
We need to compute the Euclidean distance between all the points from the cone with respect to them.
Fortunately not, because that would take us
Yeah.
forever, right? We have a method that is called closest point. It first finds the point on the object that is closest to our point, and then we compute the distance to that point. Yeah?
Yeah.
If you want to practice your math skills a little bit, think about computing the closest point on a plane to a point. If you can find the mathematical way of doing it, then you're in good shape in terms of 3D modeling skills and mathematics. Yeah?
The intersection of the vector perpendicular to the plane, the distance between.
Yes, but think about finding the exact coordinates of a point, which could be considered as the closest point on a plane to a point, which is considered as a test point. So think of it as a little mathematical assignment. Then you will get the good grasp of what it means to compute the closest point on objects, because you have at least understood one object in depth, which is a plane object, and then you can compute the closest point on that object by using dot products and so on. Okay, so do you understand this algorithm as it is written here on the slide? The kind of thing that is written here is a representation of algorithms that is called a pseudocode. So it's not a code that you can run. This is not interpretable for a Python interpreter, but it is interpretable for a human being. There is no universally acceptable way of writing pseudocodes. It's more of an art rather than a science. You are writing something that is supposed to be understandable for another human being who knows something about programming. So it's not written in any particular programming language, but it's supposed to be understandable for programmers, right? So you more or less have the concept of the scope in this code, because you have for loop and indentation, which is somewhat similar to Python. So it's a pseudocode more or less in the style of Python. You can also write a pseudocode in the style of C# or C with curly brackets, and you can make it as fancy or as simple as you want, right? But essentially, it's about giving those instructions and clarifying the flow control mechanisms. Yeah. So what's supposed to happen? After we have formed the voxels, we want to find the distance of this voxel to the boundary representation. And we want to change these distances to negative distances if they're inside or outside, whichever you want as a convention. And then we want to color the voxels as to their distances from the boundary representation. But the first question is how are we going to create voxels? I will explain that on the code itself. And how the way in which we are going to use to make the boxes around the voxels is using this method, which is going to be based on one functionality in Rhino command, which is called mesh.createFromBox, which expects the points of a mesh in a particular order in the 3D space to form the faces of the mesh. If you don't want to use this particular function, you can also write this a mesh, let's say manually with these faces. I will tell you much more about these traces and so on in the next lecture tomorrow about topology. But basically, for now, think of them as tuples of integers that tell you how you can keep these objects together. So essentially, these 6 important tuples of integers are the things that bind this box together as a box, right? So they tell you that there is a phase from 0, 4, 0, 3, 2, 1. 0, 3, 2, 1 is a phase. Yeah? It's a little rectangle or quadrilateral instance. Yeah? So basically, this is all there is to a mesh, vertices and faces, at least in terms of what it is. The rest is methods that operate in a mesh. And this should be pretty straightforward to understand. From a center point, we create these little vectors in the direction of the diagonal of the box, the components of the diagonal of the box, and we move these points to the corners, and then we connect them all together. So I will put these slides on Canvas, so you will have access to these, and also on the repository. But you already have these links to the documents. There's only one new link here, which is about learning NumPy for absolute beginners. I've also shared that link in the team space. This is from the numpy.org. So let me show you the code itself. Okay. So this is the code example that you have access to on the repository. Actually, let me show the latest version. Has anyone downloaded the file from the repository? Yes. Is it working? Yes. Okay. So this is the script component. You can find a new one by searching script. Bring it here and choose the language to from here, set it to Python, and then you are basically in. So I've written all of this here, but maybe I can start a new one and show you how to code here. Basically, this is an integrated development environment that gives you some hints. And there are some libraries that you can import, and there's another example that shows you how to import stuff. This is the other example. That shows you how you can import stuff and how you can make sure that your Python interpreter is the right version. And with this line, with this notation, you can install libraries. Almost looks like a comment, but this is the particular implementation of Python, which is inside .NET or C#. And this is how you can install libraries using pip, the integrated pip package installer for this particular Python interpreter. So this example is about installing libraries like NumPy and utilizing the Grasshopper library for making data trees if you ever need to. But I don't think we need that in this example. It's more for your information. Okay, back to this example. So this is how you can start coding here. So I can change the name of the input variables to something like solid. And I can connect it to this boundary representation, which is a cone. And I can actually, after I type something, there's a little bug with this component. You cannot set the type, unless you open this once and type something here. So after you open it and type something here, then you can set the type and say, so this object is a boundary representation. I will tell you much more about what boundary representations are exactly tomorrow. For now, you just need to know that this solid object or this cone is a boundary representation called a figure. And I want to get the size of voxels as a tuple of 3 numbers, the size in X, the size in Y, and the size in Z. And one elegant way of doing this is to taking the whole thing as one compound variable called the size as a vector. This is what I'm doing, right? I'm composing a vector to indicate the size of every single voxel. And here I can also specify that this has the data type vector 3D. Yeah. And then basically I'm in and I can verify that everything is okay. I can import the library of Rhino that geometry. This is called a namespace. Rhino.geometry. With a dot, you go to a namespace, which is the big folder in which a bunch of objects and methods are located. And we can call it RG to save some space when calling it next time. And you can start creating objects easily like this. You can say A equals RG.point3D. However, can you imagine a reason to have a point 4D? Do you see the other names that appear in here?
Yeah.
I gave you one reason to have 4-dimensional points already in the morning, right? For transformation. And what do you think is a point 3F? Is 3D about 3 dimensions or something else? So remember that I told you that numbers are represented as float numbers or double precision numbers and so on. So D stands for double precision. F stands for float or single precision. So these are about different representations of discrete representations of approximate real numbers. Yeah. So for some operations that you don't need so much precision, then you can use points with 3 floats. So now let us choose point 3D and type something. And then you play. If something goes wrong and you get an error, it will appear here, and if not, you will get the object out as a point. Let's make another object. The convenience of this environment is the excellent visualization. Make a circle, and I just know about this, but I will show you how to figure this out. Okay. So this is the circle that I just created using this component. And if you want to figure out how to work with these kind of methods, you have to get to know this library and its documentation. So this is the biggest namespace, which is called Rhino, the biggest namespace of the Rhino Common Library. This is a smaller namespace called Rhino.geometry. This is where we are, right? Rhino.geometry. With every dot, you go to a smaller and smaller namespace. And this is a circle. If you look at here, then you see a bunch of different methods called constructors. These are the methods using which you can construct a new circle. And you can see that, for instance, one of them is um, from a center, and point 3D is a type of the first object, which is called the center, and double is the type of the second object, which is a double precision floating parameter or a number, almost a real number, the radius, right? The reason this documentation is written like this is that the original code for Rhino is written in C++, and C++ is a strongly typed language, so everything has a data type. And so they always mention the data type of things, which is handy because you also need to know what you're doing in terms of the data types being passed through a method. So this is the alias or the version of the function that I'm using now. I'm putting one point as a center and one number as a radius. And the other handy thing about programming in this environment for prototyping is that you can easily check okay, I have a parameter number and I can, instead of 10, I can put R. Now I just label it, okay? So, and of course, everything about Python can be checked also here. By importing SIP and printing the sys version, you can check the version of the Python interpreter that you have and make sure that everything is correctly installed. Okay, is there something more important about this? So another library that you might need occasionally is the Grasshopper library. The Grasshopper library has an SDK, which is a software development kit, which is a documentation like the Rhino common, but it's not available online. You can get it from a command in the command line of Rhino. You can say Grasshopper get SDK documentation, which I have already done, and it's on my desktop or document. So I can open it for you to show you what it is. So again, this is a kind of a documentation that similar to the one that we just saw online. It's a little more clunky. Maybe the most important thing you need from this is the data tree, which is the kind of data structure that is specific to Grasshopper. Which I have introduced in the other example file to tell you why it might be necessary to work with them in Grasshopper. I can give you one example. Let's say if I take two lines and as a list of points and divide them into points, each to 10 points, I will get something, a new data structure, which is called a data tree. Which is basically a dictionary or a list of lists. You can see that it has two branches. paths or two keys for the two chapters of the dictionary, in each of which there are 10 points. Because this was about dividing a line or a curve into 10 points. So if I use 1 point, it propagates to 10 points as a list of points, which are the results of the division. And if I use 2 curves or 2 lines, then the results will be stored in a data tree to conveniently differentiate the results of the first operation and the second operation. So this is the mechanism that Grasshopper uses to propagate data through the wires from one component to another. And it can get more and more sophisticated depending on the next operations that you do on this thing. So I can also make lines out of this point. And then divide these lines. And now if I look at this other data tree, it has another level of depth too. Yeah. So my advice is to try to do whatever you need to do without using data trees as much as possible. If you badly need to use data trees for working with Grasshopper components, don't let them grow into higher levels of depth unless you know exactly what you're doing, and you definitely need that many levels of depth in your data tree. And if you want to work with data trees, you can refer to this example, which is here. So here I'm making a data tree of Grasshopper, DS data tree of point 3D, Rhino object, a new one. I'm making paths in it, and I'm adding points to these paths. And this is a data tree. Yeah. So to this example, okay, let me tell you something about voxels. How are we doing with time, by the way? Okay. I can explain you the process of voxelization here. So this is the boundary representation or cone object that we have, which doesn't have an inside. That is why. So now the results should be different. I just capped it. Then. Okay. Now it is clear. Okay. This is a boundary representation for a solid object, which is basically a 3-dimensional manifold space, which is only wrapped with a 2-dimensional surface, actually with 2 surfaces here. Correct? So instead of really representing the 3-dimensional set of points, you are representing its boundary, hence the name boundary representation. Right? So it has an inside and an outside. But for creating the voxels, I'm actually creating a regular grid of points. And later I check the relations to this object in terms of distance or being inside and outside. Yeah. I have written much more about voxelization, about voxelating the surface of the object or things like that. And I put links in the first notebook of this afternoon. Yeah, two papers about voxelization. So here I'm basically creating a regular grid of points inside the bounding box of the object. So what do you think a bounding box is? It's a tuple of 6 numbers that show the extents of the object in X, Y, Z coordinates. And this tuple of 6 numbers can also be understood as 2 points, 1 point representing the 3 minimum numbers, and 1 point representing the 3 maximum numbers. So which are these 2 points? And we're using a method from the Rhino geometry library to get the bounding box of a given object. Yeah. And then this bounding box is broken into these 2 points, and I'm printing them. And then I make a tuple of 3 numbers, U, V, and W, by getting the components of this size vector, X, Y, Z. Right? I'm just converting one data type to another. I want to have a plain tuple of 3 float numbers from the vector 3D object. I cannot just say equal to size, because size is an object that is specifically written as a vector 3D object. So it has to be first broken down into its essential components, and then you can assign these components to something else, right? So line 15, I'm printing the diagonal of this bounding box. What do you think this represents? Basically the sizes in X, Y, Z. Because vectors are not lines, right? Vectors are arrays of numbers. They show directions and the amount of displacement. So the diagonal of the box effectively also shows the size of the box in X and Y and Z. And then I'm transforming this one of the corner points of the box, because I need it for an embedding. As I was explaining in the morning, sometimes we need an embedding in a new coordinate system. I call it minimum corner in Z3 because I'm moving from points represented with 3 real numbers to points represented with 3 integer numbers. So that is called the space of Z cubed or Z3. In code, I call it Z3. Yeah. But right now, it should be clear to you what we mean by Z3. So instead of tuples of real numbers, we are talking about tuples of integer numbers. And that's what boxes are. They're tuples of integer numbers. Yeah. But if you want to see a voxel in a real space, in the space of Cartesian coordinates, you have to bring it back to a point that is actually embedded in a three-dimensional Cartesian space. So this sounds a little bit unintuitive perhaps to you. And that's something that you can understand by comparing the points that I'm making in this loop with points that you can create as tuples of ijk, which I've mentioned here. So these are actual voxels, not voxel points. These are tuples of ijk in this nested loop of integer coordinates. But let me get you to this loop, and then the rest will be much easier to understand. So for now, ignore this one, the minimum corner. I just told you why I'm making them. And think about the diagonal of the box in n cubed. N is the set of natural numbers. Yeah, n3 is the set of natural numbers in a three-dimensional space. So what does that mean? Tuples of 3 positive integer numbers. The difference of n with z is that in n you only have positive integers. So this diagonal in n cubed actually shows us the number of voxels in u, v, w directions or x, y, z directions, right? How am I making this? I have already formed the diagonal in n cubed by rounding the diagonal in R3. The diagonal in R3 is formed by subtracting the max corner of the bounding box, subtracting a mean corner of the bounding box from the max corner of the bounding box gives us the diagonal in R3. And then I'm rounding these numbers when after divide, they are divided by the size of every single box. So that tells us how many voxels will fit into that bounding box. Why am I rounding? Because voxels are discrete, so I only can have an integer number of voxels. Right? So basically, this tuple of 3 rounded numbers tells me how many points I will have, how many voxels I will have in M, N, O, or U, V, W, or X, Y, Z coordinates. So I can use these 3 numbers, M, N, and O, to write 3 nested loops to create these 3D points. And then I add this minimum corner to them. This is very, very important. This minimum corner embeds them in the right location within the bounding box of the object. Otherwise, they will be drawn from the 0, 0, 0. Right? This minimum voxel corner is created in 2 steps. One is that first I round the coordinates of the bounding box in the bounding box corner is Z3. Divide them by U, V, W for the voxel sizes. And then I multiply them again with the sizes. Do you know why I'm doing this? Can you imagine why I'm doing this? This is a bit of a long story that you can check mathematically on paper, but the short answer is that I'm doing this to make sure that the voxel 0, 0, 0 represents the real point 0, 0, 0. If you don't do this, then that voxel will be wrong, right? And this is to make sure that the corner of the bounding box first is voxelized properly, and then embedded back into the world or the space of R3. Yeah. And this corner is then brought here and then added to these points. These points are pretty similar to the points that I created on that plane, that oriented plane. Do you remember? Do you remember that I made an oriented plane in the morning, right? On which I could represent any points as, I don't know, S times U and so on and so forth. Here, this S is replaced with I, J, and K, S, T, or something else, right? So now I have 3 such coefficients and 3 directions. The direction is already taken care of because I'm actually putting them in the right location in the tuple for the point 3D method in Rhino. Yeah. So effectively, I have those 3 vectors, principal vectors, and I'm just multiplying them. And this is the first point or the corner of the coordinate system that I'm adding. Similarly, I added the corner or the origin of the local coordinate system of that plane in the morning. Do you remember P0? This is that P0, right? And then I add this voxel point, which is a representation, a real representation, or an R3 representation of that voxel point to the voxel points because I want to visualize it. If I don't need to visualize it, if I just need the essential data to represent that voxel, what would be sufficient to represent that voxel? You know about raster models, right? You just need the coordinates of the integer coordinates of the raster point, which is this tuple ijk. So if you ask me what is the voxel, I would say it's the tuple ijk. That is why I call them differently. I call this the voxel in N3, right? And the other one is a voxel point, which is embedded in R3 to be shown in R3 in the Cartesian space. Yeah. So if I wanted to spatially index these voxels ijk, what would you recommend me to do? If I didn't want to store all of these voxels, if I only wanted to store, let's say, the voxels that are inside or on the surface of the object, instead of the full list, I could just write down the IJK tuples and use them as keys for a dictionary. Yeah, and remove the ambiguity of equivalence between voxels, because with integer coordinates, the question of equality is very easily answered. There is no doubt that the point 235 is the same, the voxel 235 is the same voxel in whichever programming language or whatever system that we use. That is the main reason why I'm so interested in voxels, because they remove all kinds of problematic operations from geometry computing because of this absolute precision. And now, can you think of one integer coordinate that can represent a single voxel? You know about spatial indexing, right? You know about space filling curves? Do you know how spatial indexing works? No? Let me show. So this is a Z curve, space filling curve in 2 dimensions, and this is the same thing in 3 dimensions. This is something like a snake that traverses through all the possible points in this space in a very systematic way. And it has a fractal structure in the sense that if you look at it from a far distance, the same order that you see in the smallest square here is repeated in the bigger square and the bigger square and the bigger square, which is something like 0, 1, 2, 3, right? And 0, 1, 2, 3, and so on. So it effectively voxelates the space into what we call an octree. So if you compute this Z curve index for the voxels, which is something that we have explained in this paper properly. About voxels, you have this octree structure implicitly in the voxels just by looking at their indices. And these numbers are very interestingly created by weaving the binary representation of the x, y, and z coordinates of the voxels together, and then forming numbers, decimal numbers, again from those binary coordinates. So if you weave the coordinates of these pixels in binary numbers together and then convert them to decimal numbers, then you get this order 0, 1, 2, 3, 4, 5, 6, 7, and so on. And the first 2 coordinates also show that you are in this square. The second 2 coordinates actually show that you are inside the smaller square. The order inside you have 3 squares here. Yeah. And these pairs of coordinates are actually corresponding to these locations in the smaller and bigger squares. Yeah. So actually you can code, long story short, you can code a voxel as a single integer number. That could be a perfect key for a dictionary of voxels. Yeah. And that's pretty amazing. Okay, so after you encode voxels, then you can compute the closest point by using a method from the geometric library of Rhino. And we use this point to compute the distance. And then we check if this point is inside the object. And then if it is inside, then we change the distance to negative distance. This is to have more information on these distances. And then using this method that I've explained, we have a function. Def is a keyboard for functions. We create boxes for every voxel. And this is another variant of the same function that also accepts a color. We make a colored mesh box out of the voxel, and then for actually attributing colors to the boxes, we remap the numbers from the maximum number to the minimum number to numbers between 0 and 1. And we use those remap numbers to attribute colors, and here we output the color box. Yeah. The color boxes are here. I have baked them, or this is how you can take geometries or create instances from these geometries, and this is how you can get them and move them. Now I can delete a bunch and show you what's inside. Okay. Is this clear? Or do you know how to navigate this code now? Yes? Okay. As I said, the program is a little bit intensive, so I cannot go into every single detail of the code, but I think I covered the most important details. For the rest, you can always ask questions. And if there's a burning question, please ask right now. Then we change gears in the afternoon to NumPy and Geospatial 3D computing in Jupyter Notebooks. Any questions so far? Maybe there are many questions, you don't know which one to ask. But okay, start with a few questions. Don't worry. Is there any big doubt or big question that you think might prevent you from going further? No? Okay, so let us stop here and resume in the afternoon. Is there any question in the chat or no? Okay. So see you in the afternoon at what time? Anybody have the agenda?
145.
1:45.
Yeah.
Okay. Just before I forget, let me comment this one. Last thing is the Python. Yes, Python. Please pull the repository again.
I'm gonna also make another commit
Yeah.
for the workshop.
Mm-hmm.
I commented a lot of the steps.
Okay. I also pulled my
I'm gonna put that.
application, right? I have also added a lot of comments.
Yep.
Yeah. Okay, if you have pulled the repository for the workshop in the afternoon before, then make sure that you're pulling it again because we have added so many comments and lines to the first notebook actually, and a bunch of explanations. So make sure that you have the latest version by pulling through GitHub. Yeah. Okay. So, and I didn't save this. Okay, see you soon. Yeah.